All right, welcome to Lab A. We are going to measure the speed of a physics sphere. The independent variable is the initial height of the sphere. And from this height, if I measure the length of the plank, we can actually calculate this angle. Or we can put a protractor here and measure the angle. You know, that's another way to sort of think about what we're varying. We're varying the angle that the plank makes, right, as we vary the height. If we needed to know what that angle measure was, we could relate the height, which would be the side opposite that angle, to the hypotenuse, which is the actual length of the plank, and the sine function relates those two sides, right? So sine is the sine of some angle theta is equal to the length of the opposite, in this case the height, over the length of the hypotenuse, in this case the length of the rim. We're just going to sort of write down what the initial height is, okay? So the independent variable, and I'm just going to do to the height of the book, even though, well, actually, let's do up to the level there. So we're going to start out at 0.24 meters. H equals 0.24 meters. That's your independent variable, the one that we manipulate, the one that the person doing the experiment has control over that they can change. Viewers, can you hear my microphone okay, or is it like impossible to hear? This is important too, because like I make this video and I go to look at it later and they're like, oh, I can't hear a single word I said. So I try to maybe activate this Bluetooth microphone. Sometimes I have better luck with that, and other times it's like, no, that was work. Let me see. You can hear something. You want to far away from the computer, like is the audio quality you're noticing better or worse or the same? Because it should be patched in through like the speakers, like I'm wearing my microphone and it's all patched in. But then other times it's like, no, when you're away from the computer, it gets worse. So. All right, so 0.24 meters, that's H. Really tough to see. Maybe if we use sour lemon chalk, nice and bright. The most important road signs are contrasted with yellow against black, not white against black. You tend to notice that more. So this is a convention, like the quantity is a height, H, measured in meters, and the first one we're going to test is 0.24. Time measured in seconds. Okay. So your data table might look something like that, right? It's up to you to organize your notes in a way that you see fit, like your journal. You want to, write down everybody's time. You want to set your time. People will call them out, okay, as you measure it. Because we kind of want to average everybody's time. If it's just you, your reaction time might have been off, but if everybody else is kind of getting a similar value, it builds your confidence, like, okay, we're up on this. All right, so I'll ask you all to sort of call out your time data. You learn the same thing too. So you can hopefully lag it too high. But when you see the physics sphere enter, right, you start time as it exits stop. All right. 3, 2, you guys ready, right? 3, 2, 1. Time. All right, we saw a little bunker there, and that affects it, right? That affects it slightly. So maybe we should just redo that. In fact, we don't even need these anymore. Here, physics here. We'll let that stop. A few years ago, they did like a prank day, and the prank was to like put saran wrap like everywhere, and they had saran wrap around like the columns, like right out here outside my lab. And I remember going to work, and there was like, I guess the people that are involved in the prank are kind of walking this way, and I go up to it, and I like stop right in front of it, holding my briefcase, like, great. I'm supposed to get to my classroom. And they're looking at me like, go around it. Like it's like literally just like between these two, like I could just walk this way, like going around. But it's like just my person like joking, obviously. Right? It's like, right now am I supposed to do like after agitated and what they've done. Like, just go around it. And I'm like, oh yeah, I would have figured that out. I would have figured that out. You know, when I go around it. And then they're like, what an idiot that's like you gotta walk around it. Like, yeah, really not my students. You gotta get to know. All right, let's try it again. Stopwatch is ready. Ready, set, go. Made it. Fine, got it. We got one. Where do we go? 5.1. Anybody else get anything different? I don't trust a single data point, guys. We need at least two people. It's like, it's 4.95, 5.1, you know, it's around there. It's okay. Let's try it again. Same independent variable, 0.24 meters. Oh, I had to end it. I don't know. I was feeling bad. Discard that one. Try it again. Ready, set, go. Good. Time data. 5.06. It's pretty consistent. Anybody else get time data? Want to follow it out? E-learners. .76. That's 5.01. Okay, so if you all want to average those times, you say, well, that's what I want to calculate with the average of 3. So I don't want to trust 4.76. That's outlier. I'm calculating the average of the other two. It's really up to you. So our conclusion might be slightly different, but they'll basically agree. Okay, it's up to you as the scientist doing the analysis right now. What do you think is reasonable? You want to average all the time data, like 4.76, 5.01, 5.06, 5.1, or, you know, you want to drop the highest and lowest values and trust the ones in between. You know, so it's up to you. All right, now we could repeat that again, right? Check it again at the same independent variable. Repeated readings, multiple trials, is a way to minimize what's called random error. If there's some error, right? Like human reaction time with the stopwatch. By averaging multiple readings, that's really the only thing we can do to minimize random error. We can never eliminate it. All right. What I'm going to do now is vary the independent variable. That's always the exciting thing in the physics lab. Yeah. There we go. Varying the independent variable up. And so now we are at a height of 0.32. So that's actually 32 centimeters. And again, if you do the metric system, 32 centimeters is 0.32 meters, right? 100 centimeters per meter. Move the decimal point over 2, divide by 100, however you want to think about it. So we got a velocity real quick. Remember, this isn't the distance we're dividing on. This is just like what we're varying. So it's not distance divided by time here. This is the height that it started. The distance is what? Everybody remember? Well, we wrote it down. 7.29 meters, right? That's the length of the ladder. It took 5.1 seconds or whatever you averaged it to travel 7 meters, not to travel 0.2 meters. Here's the travel of 0.2 meters. Okay, that's 0.2 meters of travel. All right, well, here you go. See how quickly gravity accelerates things? It's fast. Gravity is a good accelerator. Safety first. Let's go drop this off the 37th building. Field trip. Oh, safety first. There's your pencil. Not a physics sphere. When the height is 0.32, the time it takes the physics sphere to traverse 7.29 meters is, stopwatch is ready, set. I know you saw that, e-learners. What's the time then? E-learners, what's the time? 3.99, 4.67. Anybody in class got a time? 4.21, 4.03. 4.03, 4.21, 3.99, right? Again, it's up to you. Do you want to average all of those? Do you want to just trust your measurement? Okay, so clearly, on average, it's faster, right? If it travels the same distance in less time, it's going faster. What was the calculated speed that you got for the first one? So you did 7.29 divided by whatever you did here for these measurements. You can clearly see this, right? Good. No trouble there at all. We'll meet. What do you guys get? 7.29 divided by 5.1 thereabouts. Like what? 1.3 or something like that. 1.43. You got 1.43. Anybody calculate a slightly different find out, and therefore they got a slightly different answer? Just, whatever you're calculating with, make it clear. Okay, so that thing was going 1.43 meters per second when I first go. Now take the same distance, 7.29 meters, and divide by the average time for the second manipulation of the independent variable, or your time, whatever you're doing for time there for yourself. And hopefully you can show quantitatively, yes, it's faster. I can support my hypothesis that I think it's going to go faster if we give it more potential energy. You might know something intuitively about energy being conserved. If we give it more energy initially, that energy is not destroyed, so it's still there. It shows this kinetic energy of motion. And that's related to its speed. Anybody with a published value for this one, the speed for the second one, who's got it? Come on, you learners, you can beat them to it. You can't beat Jordan to it, though. Click on the calculator there. All right, 1.76 meters per second. Are you all ready for this? To vary the independent variable? Yeah, a lot of excitement for that. You can't hear it on YouTube because it's muted, but it's got crazy here. Okay, you have it muted. All right. When there's 8 books, that's another way of varying the independent variable, the number of books. It's kind of better to have a height in, metric units. 8 books is the independent variable, which corresponds to either 0.4 meters. And really it's kind of like 6 books, 4 books, 8 books, there's like 4, 6, 8. We're just adding the number of books, right? That's another way to kind of think about the independent variable. Like as I put more books underneath my lamp, it's higher up, and I can kind of compare that. Wow, when there's 8 books, it goes this fast. So it's just kind of like, well, what are we trying to do here? It gets right to the heart of the essential question today. Why is it important to precisely define these things? Because somebody might say, hey, let's measure this thing in books per feet, and it's literally a human foot, and that's where that foot comes from. The king's foot was this long, and everything's going to be measured based on that. So everybody's on the same page. We all know what we're talking about. Okay. There's an SI unit for energy called the joule, and the joule is defined as kilogram meters squared per second squared. Okay, and so there's like seconds of time embedded in that unit, kilograms of mass embedded in that unit to get joules of energy. And we couldn't measure joules of energy in terms of like book height. Now, how many books worth of potential energy does that physics sphere possess? You could define it and talk about it that way, but it'd only be important for us. Like we're all on the same page. Oh wow, 6 book heights, we got this speed. And we can invent our own units. But then when we go to publish that, everybody else is going to go, oh, they're not using metrics. We're all kind of in agreement in science, we're going to use metrics. Okay. So the SI system, the metric system. So we've already precisely defined what a joule of energy is. And a joule is a Newton meter. It's force times distance. And so a force of 1 Newton times a distance of 1 meter is 1 joule of energy. And we can calculate how many joules of energy a physics sphere possesses at the time. And we could calculate the acceleration based on the angle, that it's at, and we could sort of relate all this stuff. Now that gets sort of beyond the scope of where we're at today, which is just the study of kinematics. Kinematics is a study of motion without regard for really what's causing the motion. So all we're doing is distance divided by time, right? We don't really care about what's accelerating it, how it's starting. We're getting it, a little bit better of an experiment by varying something. So if we want to see a change in the speed, so yeah, it kind of makes sense. The higher, the steeper this is, the more of its weight acting down the ramp, the faster it can go, it's accelerating more. But all we really want to show is like quantitatively how does the speed change across it. And we're bearing that out with some numbers, right? It's increasing in speed, as our hypothesis predicted it should. Nothing groundbreaking about the physics here, right? Like we're not going to make some great discovery today that's like, oh wow, we broke physics, which is really the goal. Find some new physics, push the boundaries of it, say, oh, we don't really understand this. It's probably not going to happen with it. I don't think we'll break physics. We might break a file or something in the floor, but the physics is pretty sound. Does anybody have a value for the third one? Somebody else besides Jordan calculating out there? You learners? My apologies about the board then. I know what I can do here. The Wi-Fi has to pick up because I'm hardwired in right now, but stand by. There you go. So the data table is looking something like that. Got the height. There you go. All right, sorry, you learners. The Wi-Fi had to pick up, and I think everybody got disconnected. When I go back and look at the recording, it'll sometimes be like, the meeting was still taking place, I'm still recording, and it's like students going, where'd you go? All right, so hopefully you can see that data table okay there. All right, what do we have for when the height was 0.4 meters, the time, what kind of, did we run that one yet? We haven't even run it yet, all right, so that's why. All right, so there's the first two. All right, let me put it back over here now. Or he does, you know, excuse me. Perspective of the bowling ball. Okay, that'll be a cool view. Everybody ready? Not my sour lime, sour lemon sauce. Scalar, sour. Here we go. Stopwatch is ready. Set. Go. That's what we're talking about. Time data. Call now. 3.68. Healers, any time data for that one? That might have been harder for you to see. I gave you a different view there. Try to keep it interesting here. Anybody else get any other time data for that one? Well, then we'll have to trust this one, 3.68. So calculate now 7.29 divided by 3.68. It's about half. It's like 2, somewhere around like not quite 2, 1.9 maybe. 1.98. Exactly what I said, rounds up to 2. A little mental math here in the morning. Now in this class, we always like 7 data points as like a rule of thumb. We're always going to try to collect 7 data points. But you know, you can draw a disparate line between the 2 points if you really want to. So we'll vary it one more time. And what we could do is plot a graph of the initial height against the speed. All right, welcome back, e-learners. All right, so I was saying we could plot a graph of like the height against the speed, and then we find out as the height increased, so too did the speed. And so we get like a correlation there. And then we might be able to predict how fast something would go if we were to put a lot of height, you know, something that I wouldn't be willing to test, but I might be able to extrapolate that based on my graph, right? So you can imagine if I plotted a graph of, you know, our independent variable against really what's dependent upon it is the time and therefore the speed. So the time is the dependent variable. And therefore the speed, because the distance traveled is staying constant. So as we vary the time, the speed varies. All right, we might expect a plot like this, right? Like as we've made the height higher, the speed went up too, okay? And let's say we're done testing at this height, okay? Once we get to, you know, 0.6 or so, that's as high as I'm willing to test. But I'm really curious about what if I made the height 10 or something? Well, then I could maybe use my data, like if I have a data point there, a data point there, a data point there, we got like 4 data points. I could extrapolate, you know, what it would be at any height, provided that this sort of holds, you know, to infinity. Like there might be a height whereby this would no longer work. Right? You can imagine I could put that physics sphere so high above the Earth's surface that it floats into outer space. You know, like it's so high up, it's above the space station. So it's not like, oh, we can extrapolate to infinity. That's not always the case, if that's part of the evidence. But we can extrapolate over a certain reasonable range of values. And so we'll do one more. The height is 0.48 meters. Hey, that's a consistent 8 centimeters of increase each time, so it's always been 2 books. 2 books is 8 centimeters, 1 book must be 4 centimeters then. Oh, I've lost my salad. Let me shop. Oh no. I have 1 day left to retirement. 0.48. Remember, it's not traveling 0.48 meters, that's the initial height. Remember what it's like to travel 0.48 meters. Everybody ready? I'll break the lab. Hypotheses? Nah, you won't break it. Okay, go. All right, ready? Stopwatch is ready. Set. Still got it. That physics sphere hasn't beat me yet. Time data. 3.41. Anybody else? New enters? Did you get the accurate time data there? 3.31. I feel so much better about the time data when there's at least one other sort of point of corroboration. It's like, what if you just slip your finger, you know, like get that data, do the reaction time. Feel much better about, you know, multiple data points, right? Many timekeepers. And so the average these two would be what, 3.36 seconds, because they're like exactly 0.1 apart from each other. So what is 7.29 divided by 3.36? 2.17 meters per second. If you were to get a piece of graph paper and plot these quantities on the, now we typically put the independent variable on the x-axis. There's no rule that says we have to, that's just what we typically do in science. So we'll put this on the x-axis against these quantities on the y-axis. And so I think the way I just showed it to you was the opposite. Okay. So if we plot this on the x-axis against these quantities on the y-axis, we'd be able to sort of make some other conclusions like, well, what if we ramped it all the way up to 1 meter? Okay. So here's what I'd like you to do. I want to make this clear sort of for everybody. So I want to spell it out. Stand by, you learners. This has been the data collection. Tune in next time for the analysis.